This is Section 1, or Part 1, of Section R.8, Nth Roots and Rational Exponents. The principal nth root of a real number a, where n is greater than or equal to 2 and is an integer, symbolized by the nth root, we see with the radical over the a, is defined as nth root of a equals b, means that a to the is equal to b to the nth power. So in other words, let's make a number example. The square root of 9 equals 3 means 9 equals 3 squared. Okay, so just using numbers we can make that make more sense. Excuse me. Where a is greater than or equal to 0, so it's not 0, it's not negative. B is also not 0 or negative. If n is even, and a and b are any real numbers if n is odd. So a and b have to be a positive number if our root is an even root, square root, fourth root, sixth root, eighth root, etc. But if we have an odd root, cube root, fifth root, seventh root, a and b can be any real number. Why do a and b have to be greater than or equal to 0 if n is even? And that's because the even root of a negative number is not defined. Okay, so we cannot take the square root of -4, for example, in the real number system. All right, the symbol, nth root of a, is called a radical, and the integer n is the index, and a is called the radicand. Okay. So in example 1, we want to work with nth roots. So what is the square root of 121? Well, let's think about it this way. That's the square root of 11 squared, which then is just 11. Now look at this one. It's cube root, it's odd, and that's a negative number. But we said that's okay. It could be any if it is odd. So let's see how this one works out. We can write that as the cube root of -10 to the third power. -10 times -10 times -10 would be -1000. So this is -10. And then we have here the fourth root, an even root of a negative. Well, we just said that the even root of a negative is not defined, so the answer to this is not defined because it's not a real number. Okay, let's look at the properties of radicals. Let a and b represent real numbers, then we have the following properties. The nth root of a times b can be written as the nth root of a times the nth root of b, and we'll see examples of where we'll need to use this property. You can use it to break it apart, like I've just done, or to pull these two together into a single radical, just depending on what you need to do. The nth root of a over b, then, is the nth root of a over the nth root of b. And again, we may want to split it up like this, because say the numerator is a perfect square, the denominator isn't, or something like that, and we're doing square root. Or we may want to pull it all together under a radical. And then finally, the nth root of a to the m can also be written as the nth root of a, do that part first, then raise it to the nth power. So you can raise to the power, then take the root, or take the root and then raise to the power. The order of those two things doesn't matter. So let's look at example 2 where we're simplifying radicals. All right, to simplify the radical, we factor out the greatest perfect power of that particular index and then simplify. This is square root, so I want the largest perfect square factor of 50. and that would be 25. Because remember the perfect squares, you may want to have a little list, but 2 squared is 4, and 3 squared is 9, 4 squared is 16, 5 squared is 25, so on. So I know that 25 is a factor of 50, and now because of this property right here, it says, well, then I can take the square root of 25 times the square root, I'm going to write that, square root of 25 times the square root of 2, because that property holds, and the square root of 25 is 5. So square root of 50 can be simplified to 5 square root of 2. Well, what if we throw in variables? So we're going to do the same thing here with our 48, but we've got to think about variables. Again, we have square root. So the perfect squares when it comes to variables are, well, we have x to the first squared would be x squared, and x to the second squared would be x to the fourth, and x to the third squared would be x to the sixth. Just coming up with a list of perfect squares with variables, and so on. X to the fourth squared would be x to the eighth. So I've got my little list here, and I want to look for the largest one in x to the 15. So let's start with our 48. Perfect squares are over here. Any of these, what's the largest one of these that would be a factor of 48? This is where your calculator is your friend. Take 48, start dividing. 48 divided by 25, no. 48 divided by 16, yes. 48 is 16 times 3. Now our x to the 15th. Well, what we're seeing in this pattern here is even numbers. So the highest even number would be 14, but I still have another one left to make 15. X to the first. X to the 14th times x to the first would be x to the 15th. Okay, so again, because of this property, we can break it up into pieces. We have the square root of 16 times the square root of 3 times the square root of x to the 14th times the square root of x. Square root of 16 is 4. That one I can do. I can also take the square root of x to the 14th because we said that's a perfect square, and that would be x to the 7th. And then the 3 and the x will stay under the radical. So simplified, I have 4x to the 7th times the square root of 3x. Okay, let's look at part C. Again, breaking down our 12 perfect square factors. Obviously, only 4 will work. 4 times 3 is 12. X cubed, the highest even, would be 2, but I still have another x. Y to the 5th, the highest even, would be 4, but I still have another y. Now, without writing them individually, let's just take the square root. Square root of 4 is 2. The 3 is going to stay. Square root of x squared is x. The x is going to stay. Square root of y to the 4th is y squared, and the y is going to stay. So let's write what we said would stay, 3xy. Okay, we'll finish example 2 in the next video.